So that integral over u that I said is just a constant. That constant is pi. So this limit sine squared omega t over 2 divided by omega over 2 in the limit as t becomes very large does become 2 pi t Dirac delta omega, or pi t Dirac delta omega over 2. The reason why I write it in the second way is what is multiplying t in sine is omega over 2. So whatever that it is there, it's the argument of the Dirac delta. Well, I don't really know why this argument over here fails. Well, most probably because that exponent oscillates very fast. And remember, this derivative should be a real number, so basically there I have not the exponent but the cosine of omega t when t is very large. Since that function of t is very large, it oscillates between -1 and 1. Probably you should put the average value, not the value 1. The average value will be, well, even that doesn't work. The average is 0. I don't really know why this doesn't work, but the correct answer is 2 pi t times Dirac delta because of this integral. Well, this is the actual rigorous derivation. The other ones are kind of hand-waving arguments why it should be so. Let me just do one more derivation, if you like, keeping the etas. This is 1 over I omega minus I eta times e to the power I omega minus I eta times t. This is t prime. We should take the absolute square of this quantity. Well, this is e to the power eta t divided by omega squared plus eta squared. And remember, I'm interested in taking the time derivative of that square, which will be eta e to the power eta t divided by omega squared plus eta squared, the time derivative. And the integral over omega of eta over omega squared plus eta squared from minus infinity to infinity would be pi, independent of the value of eta. And keep in mind that eta over omega squared plus eta squared goes to, if omega is non-zero, it just becomes 0. In the limit eta goes to 0. If omega is non-zero, it just becomes 0. And if omega is equal to 0, it diverges. Again, this is the definition of a Dirac delta. One property of the Dirac delta function, not necessarily the definition. So it is such a function that it is 0 everywhere except on one point, where and it diverges at that point, and its integral is finite. So this again kind of proves that this goes to pi times Dirac delta omega. So this is probably 2 pi Dirac delta omega. Whichever one appeals to you more. This is, of course, the first term in our expansion. Now let's calculate the second term. You see, this is my expansion. I had all terms here. Let me look at what I would get from this term. Now, keep in mind that, you see, I looked at CFI, then I took the square of CFI. CFI turned out to be this weird function sine squared divided by whatever that thing squared. And at the end of the day, I obtained the transition rate to be proportional to VFI. Oh, sorry, this is squared. Because CFI is the matrix element squared. But remember our time-independent perturbation theory. There we had defined this function t, which was v plus v1 over e minus h0 t. This was the definition of t. And then this is the first term. The transition matrix element TFI is equal to VFI plus other terms. Well, this is just that same number. This is kind of a hint that maybe they might be related somehow. But let's see the relationships. Now you see, if you look at Schwartz, it doesn't discuss this derivation. It just puts some energy conserving Dirac deltas here and there. That I don't like. That's why I'm just carrying out all this thing. This Dirac delta over here is the energy conserving Dirac delta. But will I get that Dirac delta from the second term? You see, the first term had this, the integrand had this dependence, e to power I omega t prime. If I look at the second term, well, it will have some more complicated expression. Let's calculate it. Well, let me find that expression. Let's try to calculate this one and see if we can relate it to our earlier perturbative expansion. Well, I didn't use the time ordering here because I already know that I didn't write the 1 over 2 factorial in the expansion of the exponent. I also omit the time ordered product because this term, remember, this was the original term we obtained. And we had written this as the time ordered product divided by 2 factorial. That I'm avoiding at the moment. So let's insert a complete set of energy eigenstates. Well, then what I get is minus I squared from t0 to t dt1, from t0 to t1 dt2, and t are minus infinity. And then I have T1, and I have a sum over all these intermediate states. Well, we had already calculated what each one of these matrix elements are. This is e to power I EF minus En of T1 plus eta T1. And the other one, e to power I En minus EI of T2 plus eta T2. I can evaluate the T2 integral explicitly, and of course I have the VFN, VNI, which will be minus I squared, sum over all intermediate states, from minus infinity to t dt1, e to power I EF minus En of T1 plus eta of T1. And then the T2 integral will just give me e to power I e n minus e I of T1 plus eta T1 divided by I e n minus e I minus I eta. This is the result of my T1 integral. Now I have the product of two exponents. The first exponent contains e to power minus I e n of T1. The second one contains e to power I e n of T1. They cancel. What I obtain is minus I squared sum over all n from minus infinity to t dt1 e to power I e f minus e I of T1 divided by I of e n minus e I minus I eta. This is v f n, v n I. I just set the eta to 0 in the exponent. Well, it's kind of shaky, because you see there I get 2 eta T1. Not eta T1, there's a factor 2. But remember, eta is a very small number. Eventually I will set eta to 0. Whether that is 2 eta or eta doesn't really make any difference. So this is the second order term. Versus the first order term was this one. That this was the first order term. Well, I can just add them up. VFI plus yes, there is I here, minus I squared over there. There's a minus sign. There's just a single factor of I, which I took out. Again, I remind you my expression of T from our non-perturbative, time-independent perturbative expansion. V minus V1 over H0 minus E V plus higher order terms. This was what we had used before. Well, I basically get the same thing. So this is, let me call that TFI, transition rate. Okay, so that doesn't, except on that eta factor over there, which in the limit as eta goes to 0 will not contribute. Well, there is no time dependence in TFI. So this integral gives me energy conservation. So the rate of transition, which is d by dt of probability of transition from initial to final state at the time t, is actually given by 2 pi Dirac delta omega TFI squared. Again, we are kind of going back to what we had done in the time-independent case, but now we are deriving that result within a time-dependent framework. There is this overall time dependence, which will, in fact, to all orders, it will give me energy conservation. And What is multiplying that energy conserving Dirac delta is a well-defined time-independent transition matrix element. So any questions up to here? Well, if you look at Schwartz, so remember this is what we had defined as our S matrix element. This is the final state in the Schrodinger picture. This is our initial state, again in the Schrodinger picture, e to power well, see, there's always a 1. This is SFI. When you can convert it to interaction picture, there will again be an exponent. And that exponent will be expanded. There is the 1. And there is all the rest. And what he does is he puts here 2 pi Dirac delta omega. That's the energy conserving Dirac delta over there. Is it wrong? Well, not really wrong, because if you take the limit as t goes to infinity, set eta to 0, that gives you the Dirac delta function. But then you need to take the, when you calculate the probabilities, you need to take their squares. So you get Dirac delta omega squares. But Dirac delta omega squared is Dirac delta omega times Dirac delta 0, let's say. Dirac delta 0 is not such a nice thing to have. But remember where that Dirac delta 0 comes from. It is the integral from minus t to t dt. So that is actually 2t. So my system started at minus capital T, and I'm looking at its evolution until plus capital 2t. The total probability is proportional to 2t. What we are interested in is probability per unit time, so we need to divide by 2t. So he cancels the 2t. But I find this more rigorous. That's why I wanted to go over this derivation. Well, does that make sense? Well, if you look at it from the package perspective, you see, I'm sending packages. There's no scattering then. The scattering happens for a very short amount of time, actual scattering. So scattering per unit time, I mean, dividing by 2t, to me, it doesn't make any sense. But if you use plane waves, that's what we are actually doing here, it does make sense to divide by 2t, because remember, plane waves are everywhere. So they cover all the universe. So some of it is already in the scattering region. So the scattering is constantly happening for those plane waves. So starting from minus t up to final time t, there's always scattering going on. And hence the transition probability, since you are looking at the transition probability from minus t to t, you should add all these probabilities, all these amplitudes. So you should add all these probabilities, probability of scattering at a given time. So that's why since the transition rate we expect it to be, since nothing is actually changing in plane waves, the potential is the same, the plane wave is the same, it's everywhere, the transition rate should be constant. So the probability should be proportional to the time. That's what we have been finding all the way around. So the rate, the probability increases with time, but the rate is constant. Because the rate is constant, it is increasing with time. And since for plane waves, the scattering happens at all times, so the total probability will be just the probability rate, which is constant independent of time, multiplied by the total time, which is 2t. So again, you can obtain the probability transition rate by just dividing by 2t.
final, since the rate is constant,
Yes.
so initial energy and final energy are the same.
No, you see, there is this Dirac delta omega. It comes from you are creating your system at a very early time and you are looking at the system at a very late time.
Yes.
If you do this, the energy is conserved. And during this time, you are not looking at what happens. During this time, the transition rate should be constant because potentially the same. The wave is everywhere. You don't need to wait for the package to arrive at the scattering center. The wave is everywhere, so the transition rate is constant for this process, independent of time. So the total probability, which we calculate over here, which involves this Dirac delta omega squared term, it's actually, we have to divide that by the total time to calculate the transition rate, which is 2t, which in the limit as t goes to infinity is Dirac delta 0.
I mean, before we are taking the derivative, there was a t in front of our integral, I mean, the result, in the result. So it means that, how can I say, energy is accumulating actually?
Not really. You see, you have all these waves,
Uh-huh.
all these amplitudes, independent amplitudes in a sense,
I see.
summing up. You are summing the waves, the amplitudes, not the energy.
Okay.
So that's why I wouldn't say that energy is accumulating. The wave is accumulating, if you
Waves.
like. Right. Any other questions? Now, let me look at one more thing before we call it a day. You see, I said that we are looking at the final state different than the initial state. What happens if they are equal? You see, this whole derivation, we will have problems well, EF is equal to EI if the final and the initial states are the same, so we get all these divergences. So this results, we cannot straight away use them. But still, it's not really a big deal. What I would like to calculate is ISI, let's say. Well, I know what my states are. My state at some later time, let's say t, is I minus I over h bar dt prime from minus infinity to t, vi of t prime, I plus higher order terms. What I'm looking at psi of t I. Let me leave the time t0 to avoid some infinite expressions. This will be 1 minus I over h bar from t0 to t dt prime I vi of t prime I. Well, this is in the interaction picture, by the way. This is just VII, the diagonal element. No exponents, nothing. This is just 1 minus I over h bar VII of t minus t0 plus higher order terms, which is e to power minus I over h bar VII t minus t0 plus some more corrections, or all those corrections I can also put in the exponent. this one. What is psi in the Schrödinger picture? Psi of t. Well, it is psi of t in the interaction picture multiplied by e to power minus I h0 of t minus t0. Initial state psi of t I times the initial state plus all the remaining terms. Yes, I'm just using the identity, just picking up the initial state. I already calculated this one. This is, well, let me, okay. H bar is 1. E to power minus I EI plus VII times t minus t0. But you see, what does this tell me? The energy of the ith state is not EI, but EI plus VII. Yeah. Yeah, not strictly, but you see, let's say that, let me put a 0 over here, denoting that they are the eigenstates of the unperturbed Hamiltonian. I is the eigenstate of the full Hamiltonian. I0 is the eigenstate of the unperturbed Hamiltonian. And keep in mind that we are doing some computation up to orders V. To this order, this is equal to of course, I will get corrections, other terms, but the up to V, that is also the corrections to I will be proportional to V, let's say. Now, what does this tell me? Well, the ith state has energy VII. This is nothing but first order correction to the energy eigenvalue. Now, where do we get this? We derive this from this scattering. Okay, the terminology, we call everything that involves the interaction with the potential a scattering process. So this is a state scatters into itself. It doesn't scatter into another state, but it scatters into itself. So this is called the self-energy. Okay, in field theoretical framework. For example, we had already looked at our potentials, which was given by lambda d cubed r phi 1 we had already identified some diagrams that might contribute. We looked at the scattering of two particles off to some other final state. Now, we can also look at, for example, K1 scattering into K1. The first type 1 particle. Well, this is type 1 particle. Again, if you remember this expansion. This is t. This is just s is 1 plus it. This is just corresponds to this 1. Then I have plus, well, the v, that v term, will create a second kind of particle or annihilate it. In my final state, there is no second kind of particle. In my initial state, there is no second kind of particle, so that will be 0. This one will be, there is a potential vertices here and there. It will be such a diagram because one of the v's, it should, there is no second kind of particle in my initial state, so it cannot annihilate. Then it should create. It creates a second kind particle. Then the other v should annihilate it because I don't have that second kind of particle in my final state. So this is what I would get, this diagram. Now, if I wanted to calculate the contribution from this diagram, well, you see, at each vertex I have a lambda that I had already calculated. Then there is the, let's say this is K1. And if you remember our earlier derivation, we had, let me call this K2. We had integration over all intermediate momenta, but at the same time we had momentum conserving Dirac delta functions. So let me just use those momentum conserving Dirac delta functions. So this is K2. If that is K2, the momentum of this second kind of particle should be K2 minus K1. Here I have K1. The resulting integral will be, you see, K2 is not fixed by momentum conservation. All three momentum in all vertices, they are conserved. So since K2 integral is not conserved, I have to keep an integral over K2. I cannot avoid that. And then I have the propagator of the intermediate states, which will include, let's say, K2 minus K1 squared minus m squared. Well, in our previous derivation, we didn't need it. Well, we will make more formal derivations of that result. So this is the propagator of the second kind of particle. This K2 minus K1 is its momentum, for momentum. But I should also add the integral squared. This is the propagator for this particle over there. Their masses are different. Again, I repeat, we will make a more formal derivation of this result. But now we have a problem. You see, this integral will be an integral over the magnitude of K. Well, it will include the integral over the directions of K2, but it will also include the integral over the directions of K2. Now, there will be regions where K2 is very large. There's no limit on the momentum, so it can go up to infinity. But if K2 is very large, then I can just ignore K1 relative to K2. I can ignore M1 and M2 squared relative to K2 squareds. So this will be K2 squared divided by K2 to the 4. The contribution from very large values of K2 will have this form. But this diverges. So you see, we had already seen one divergence, which we just throw away. When we were calculating the Hamiltonian. Remember, these are the fields. We are just describing the fields as infinitely many harmonic oscillators. Each harmonic oscillator has a ground state energy, and the ground state energy is h bar omega over 2. And we are summing over all these h bar omega over 2s for all possible values of omega, for all our oscillators. Well, that diverges. That is infinite. So the energy we obtain actually has an infinite constant. But then we said we could easily say that, okay, there's also potential energy there. We are not actually measuring the exact value of energy. We are just measuring the energy differences, and that constant, although it is infinite, in differences, it will just cancel. So it doesn't have any consequence, that constant. It is if you are doing gravity, it does have important consequences, but for us, it won't have any consequence. But now we have another divergence. So if you would calculate the self-energy of this particle, it will also diverge. And that is something we have to get rid of somehow. Well, this divergence actually also exists in classical physics. Just imagine the single electron, single point charge. A point charge has electric field magnitude equal to Q over R squared, which has an energy density. Remember, energy density in an electric field is 1 over 2 epsilon 0 E squared. So this energy density is actually proportional to Q squared over R to the 4. If you integrate this energy density over the whole volume, this diverges. Yes, even in classical physics, we do have such a divergence for point charges. So here we are looking at a point charge, actually, essentially, and it has a divergent self-interaction, self-energy. Well, we will get rid of it in the next term. You see, the basic idea is, again, just is how do we get rid of this divergence in classical electrodynamics? No, we just say that the electron is not a point charge. It has a finite radius. And then we say we just calculate this energy, self-energy, or in the electric field created by it, and equate it to its rest mass energy. So that also tells you the classical radius of the electron. So basically we are saying that all the mass of the electron is due to the electric field it creates around it. So that is the way we avoid this problem in classical mechanics, or we look at continuous charges. There you don't get this problem. And well, we have ways of getting rid of that also in quantum field theory. But just to keep in mind, we are seeing these divergences appearing here and there. They will appear even in other processes. So any questions?
What is the meaning in that divergence in quantum field theory?
Well,
I mean, physically.
Well, we will see that. So the problem here is we are doing some computations. We are basically describing some picture. That picture is not unique. So what we will show eventually is if you are able to express one measurable quantity in terms of other measurable quantities, everything will be finite. In the intermediate steps, you do get divergences.
At the end.
But at the end, once you express observed quantities in terms of observable quantities, everything turns out to be finite. So it basically tells us that there is a problem in our computational method, but we are able to live with it. But this is not valid for all theories. In some theories, you cannot do that. Then we say that, okay, those theories, we cannot make sense out of them. Any other questions? So let's end today. I mean, we have 5 minutes left, but it doesn't worth starting a new subject. So let's end here, and we will continue next week.